welcome to Data Science Conference. Today we're going to take a look at the origins of machine learning and deep learning and see how it can be benefited for all the audience in terms of gearing up for the future data science platforms and getting into the field of data science education. So this would be something that like you'd be looking forward to understand the prerequisites required for getting into data science and what are all the components of data science or machine learning that we need to have, including prerequisites of calculus and linear algebra as well. And we'll go step by step here, and we'll also try to understand a little bit more about the origins of neural networks as well. And whenever you have any questions or any clarification that is required, just feel free to send a question on the Crowdcast platform here. So you have a Q&A window where you can type in messages so that we can get the clarification right away on those. So let's take a look at this deep learning and machine learning. So as we know that statistics has been there for a while and has been embedded into the deep learning and machine learning algorithms. But at the same time, it's also important to see how the automated rules that were created at some point in time earlier, and then we had a lot of issues with these hash-coded rules for implementation, because, for example, we have a million rules that we need to encode to be able to make a decision in terms of how a vehicle has to navigate, or how we need to get a response from a particular environment. So it's going to be very complicated with all those rules, because what if we have something that comes up at a runtime that's not covered with those rules? And so that's where we had issues with earlier types of deep learning and machine learning implementations, where it was more of a rule-based type of algorithms, and even the statistics had a fixed way of implementing particular rules. Then the machine learning and deep learning has advanced to another level where we could have something similar to mimic the architectures of a human brain that can give us understanding of how we can translate that into a neural network architecture, so that we can take advantage of the neural networks, the way the human brain processes all of this information at runtime, and basically comes to make a decision at each step of the neural network. So that's how the neural network is constructed. And again, the neural networks in earlier times, like if you look at like 60s or 70s and sometime of that frame, we had a lot of challenges in terms of adopting these neural networks, because it was like we are not even having deep neural networks. Those are just machine learning neural networks where we have limited number of neural networks. So the input that we could process through those nodes is minimum, as well as the output we get also is going to be restricted because of the size of the neural network. Back in those days of earlier decades that we have, and then coming to the like if we see advancing to the 90s, like there are a lot of far more techniques that have been built as opposed to earlier times of neural networks. And in the recent times, we can see like the AI is embedded everywhere in our daily lives here. So basically, if you want to see like in your smartphones, you have speech recognition, and then you have neural translation architecture and everything that you want to find out, like you want to understand particular, how something works and anything, that you have a whole lot of neural translation architecture embedded into search engines, and then you have generative AI with ChatGPT and large language models called the LLMs, where you can process any number of data sets to be able to power the AI with the type of intelligence that is needed to give the results that you're looking for. So that's when, like in the recent times, when we come from earlier, like in the 90s, like you have Bayesian neural networks, and then a few other techniques that came up. But like in the earlier 2000s onward, we started seeing another trend with deep learning neural networks. So we're not just limited to a set of neural networks anymore. So we have large scale neural networks that could, basically have any number of nodes, and then any number of neural network layers and processing nodes for each of these deep neural networks. So you have like millions of neurons, and now you can galvanize the industries such as like bioinformatics, or you can have the chemicals or drug discovery industries, so on and so forth. So it has been embedded into every type of industry, or you're looking at retail, utilities, energy. All of the energies have been able to take advantage of these thousands of processing nodes, so that because you have such large data sets, as opposed to be before the advent of big data we had in the 90s, there were no big data or anything like that. So that's when you are not having so much of information. Now, the companies that are operating on digital platforms such as e-commerce platforms, or they're running any like PayPal or any other Silicon Valley-based companies, they all embed reinforcement learning and deep neural networks in their AI environment, so that they're completely operating on that. And if you also look at the IoT data stream architectures, where you have devices placed on the warehouse environments for movement of the objects, or where you need to be able to deploy some robots to able to move the packages from a location to another location in the warehouses. So all of that has been now implemented with IoT sensors and deep neural networks and reinforcement learning, where the decisions can be taken at runtime rather than a rule-based algorithm that were leveraged in the earlier times of neural networks. So let's take a look at how this neural network even works, to see, we know that we're not going to be going to super complicated advancements in this session here, considering the audience are more geared toward to be data enthusiasts, and they would like to be data scientists of the future. So we'll try to make this as simpler as we can, so that we'll try to understand in a way which is easier to ingest and process. And then if you have any questions, feel free to just be here. So basically, if you see this is a very simple neural network we are looking at here. So we have an input layer, and we have few hidden layers here as well, and then we get an output layer here that will contain the result from the calculation of the input layer, processing of the neurons, and then further processing through the hidden layers, and then we get the actual output. So this works much similar to the brain functions that we have, where the neurons are connected. Like we have, the human brain contains like a 100 billion neurons that can orchestrate with each other in a very extremely fast manner and very advanced way, so that we get the information processed from a node to another node. So that's how the neural network is constructed to be able to get to the future of data sciences, which is what everybody's expecting, something they call as AGI, which means like artificial general intelligence. So in case of artificial general intelligence, the machine should be able to take complete decisions on their own, and they should be able to make decisions at runtime rather than through the rule-based mechanisms and probabilities that will give them some statistics that could allow to only work for a few scenarios as opposed to cover runtime scenarios. Just for example, we have self-driving vehicles in this decade here, and these self-driving vehicles that we have basically help us to navigate. And again, you have LIDAR in it, light detection and range technique, that will give you the distance of the object located on the vehicle, so that the vehicle can prepare if they're approaching pedestrians on the intersection, or they're able to dodge the pedestrians and get around it rather than colliding with any of the other side of the spectrum of the traffic intersection. So how is that all happening? So basically, the entire neural networks are orchestrating at runtime, scanning for objects that could show up at out of nowhere, appearing on the radar of the AI spectrum here, and then they are able to basically navigate through that and make a decision on how exactly they need to be able to go through that. So that's how the reinforcement learning algorithms are built, and they will give us a lot of constraints in terms of how to navigate through unknown landscapes, such as like if we are going to send a spacecraft to Mars, for example, the gravity or the landscape is not known at that time because it's completely unknown where the landing is going to happen. And so basically the spacecraft needs to have the reinforcement learning algorithm to be able to adapt to that environment at runtime and then make those launching decisions to land across the Mars planet there. So, so that's how these algorithms are implemented. So here, if we just take a look at this, so we have a network connections here between each layer, and the network connections basically contain processing nodes, and processing nodes are connecting from an input neuron to a processing hidden layer neuron, and then subsequently we get a result out of it. So that's how we are seeing here. So, so basically, if you want to take a look at this, we spoke about earlier, earlier there was only machine learning, and then subsequently the deep learning came up, which is basically a branch or a subfield of the artificial intelligence, part of the hierarchical machine learning. And so how all of these deep learning constructs came together, like you're looking at Boltzmann restrictor machines, or you're looking at autoencoders, or variational autoencoders, generative adversarial networks, or the generative AI, LLMs, natural language processing, object detection, or speech recognition, or machine translation techniques. All of this came as part of the deep neural network. So deep neural network started, and then there are a lot of constructs of neural networks, like we have recurrent neural networks, and we have convolutional neural networks, and stacked autoencoders, and so on and so forth. So each of these has been applied to various industries. For example, like a stack of autoencoders is applied for genomics, to basically discover new drugs and understand the cause of the, what's happening inside the gene, and how to resolve the challenges that humans come across in terms of understanding, the whole orchestration of genome in humans. So that's how exactly the stack of autoencoders have been applied for various industries. And basically, Orbus has created a thesis, and he has come across, put forward with deep neural networks and with implementation of gradients, and that was like 48 years ago. And then we have gradient forward propagation and back propagation algorithms for training our large-scale neural networks. And so that's when it's not just the neural networks we're talking about. We also need to have some sort of a scalable hardware, like we need to run like GPUs or CPUs or any other types of unified hardware memory platforms, in-memory computing platforms that can actually allow operators to scale at a larger scale. For example, if you look at Los Alamos lab, at that place, basically they constructed all the simulations of how the atomic bomb should appear instead of actually blasting it out. And they used to create holes in the islands before, but no longer. So ever since they invented this Fermi acceleration through the hardware and deep neural networks, so basically they simulate the explosion of atomic bombs or things like that, and then they would be in a position to basically come up with the trajectory path of how it's going to go and what kind of impact it's going to have, what kind of a chain reaction it's going to create. All of those are now possible in today, or if you're looking at plasma turbulence, because there are a lot of other implementations that are going on at Los Alamos for basically the recreation of the temperatures where solar energy can be leveraged through nuclear fusion or nuclear fission and some other types of plasma turbulence activities to power the Earth with those type of neural network architecture. So all of this is implemented in the labs here, and they're also implemented for several other healthcare industries as well for taking care of that. And all of this is possible with neural networks and the gradients and forward propagation and backward propagation type of implementations that will that are scalable and highly available for each type of technique of implementation. So here we're just going to take a brief look at this neural network we're looking at is a simple neural network that contains like few input neurons like here, and then we have processing layers, which are also known as the hidden layers, and then we're going to get outputs on the output layer, and that will give us the actual calculation. So to be able to implement any backpropagation algorithm in a neural network, either it's in PyTorch or Python, because if you leverage PyTorch, you have few packages already available for you to compute few of the forward pass or backward pass computations. But if you're going for Python, it's going to be just bare NumPy that you're going to have to leverage and implement all of this. And basically every neuron, to activate it, you need an activation function. So which is like here we're going to leverage an activation function called a logistic function, and that's how we're going to leverage it. And we're going to initialize the weights and assign some random weights for each of these neuron here. So it's going to compute, and it will calculate the net input for each of the processing hidden layer here. For example, we want to calculate the net input y1, and then we're going to multiply the weight 1 by input neuron and add that to the weight 2 and multiply the other neuron. And we're also creating few bias nodes here, so just so we are assigning some bias values as well to eliminate any bias in this whole neural network. So we're going to get more accurate outcomes here without any bias in here. So that's why we're also taking care of that. So we're going to maximize the accuracy of this neural network by basically assigning the weights to it, and we make a forward pass, and we make the computation of net input y1 and net input y2, and then similarly we're going to accumulate for the net input of y2 as well. So we see that a few values have been computed for both y1 and y2, basically, which are nothing but the hidden processing neurons or the processing layers of the deep neural network. So again, as I told that, we're going to apply the logistic function here. So the logistic function is basically an activation. So you're going to activate a neuron. So that's how you're going to apply the activation function. And so let's see like how we're going to be able to. So this is the activation function we're talking about here. So 1 by 1 plus e to the power of net. And then ultimately we want to calculate the z2 here, which is basically is going to be computed with net input z2. And so basically that will be the weights that we're going to calculate for net output of A1 and net output of A2, and then we also take care of the weights surrounding each of that, and we also add the bias nodes just to improve the accuracy of this algorithm, and we're going to get the computer net output output for this output layer as well. And we also are going to compute, because the entire purpose of calculating is back propagation to get the maximum accuracy here. So we're going to try and run through the whole network to reduce all the errors there, so that we're just going to have a little bit of calculus and algebra here. So we're going to apply this error formula here, and then we're going to just compute the error from each, and so that we're going to be able to avoid any errors coming across from that. So then we're going to apply something called chain rule from the calculus, which is a differentiation function. So chain rule is basically a differentiation of function of a function. So we have a function here, f of z, which is cos z of z of z, and then we're going to compute a function of a function, which is f z of z. So that's when we are able to differentiate the function of a function to the chain rule. So let's take a look at this chain rule for differentiation here. So it will be dx by dz is dx by dy multiplied by dy by dz. So we're going to see the derivative of each function and how we're going to calculate that. So basically we're going to now take a backward pass here, and then we try to compute the error, and so that we can have a very highly accurate outcome or result from here. So we see that we went through this formula here, and we are able to now get a more accurate output here. So we are now optimize and improve the accuracy of the result here. So now we're going to take a look at the what we call the singular value decomposition, or also known as the billion-dollar algorithm. So why we call it that way? Because all the billion-dollar industries leverage this algorithm in every type of industry they run. For example, you look at Amazon. So Amazon has a whole recommendation system they built for recommending the books for you, and how is it able to identify when you purchase a book that they need to recommend you another book similar to that, or something that piques your interest. Or if you have like Netflix, for example, they perform a lot of text mining based on all the ratings you give and all the feedback that you give, and then it's going to compute recommendation system for that through the text mining, and it's going to come up with a recommendation system for that. So that's basically the singular value decomposition. There are several other industries that also leverage this particular algorithm, such as the singular value decomposition. So basically, how are we going to be able to implement that? So this is pretty much in your alley here, because this is simple linear algebra that you might already be applying at your education level currently, and you should be able to compute this similar to how you compute your the prerequisites of a little bit of linear algebra. We're going to take here, and then see how basically we're going to build a fundamental theorem here, and we're going to build a few matrices, and we compute the matrices as the product of these three matrices here. So we're going to compute the x is equal to u of sigma of v of t. So basically, so we're going to take the orthogonal n by n matrix, and then we're going to take a diagonal matrix of size n by p matrix. We're going to take an orthogonal matrix of size p of p, and then we're going to basically come up with a BT, which is nothing but a transpose of the matrix, which is the orthogonal p by p matrix. So it's a linear transformation of the geometry, which is a composition of essential actions that we need to take here. So basically, we're going to look at how we're going to perform this computation for factorization of the original matrix into multiple matrices here. So you can take a look at here. We have a data matrix here, and we have left singular vectors, and we have a diagonal singular values, and we also have right singular vectors as well. So you can compute this for basically for anything like for words, or usually it's a heavily words, because based on the reviews on Amazon, people buy the books, and then you also write a review for that, or you can choose another book. So you may so all of that word occurrences of reviews and the common interest for making a recommendation across multiple books, you're going to be able to get that from our Amazon recommendation system, leveraging the singular value decomposition algorithm. And it's not just, you can apply for any such systems where you have natural language processing for, computing the embedding of the words, and so on and so forth. So here we're going to be taking a simple case of example. We're not going to be taking like a large scale a data set that comprises a lot of text values and stuff like that. So we're going to just take a simple rank 2 tensor data matrix for our example here. So the single value composition, I'm just going to create a simple rank 2 tensor here. So rank 2 because we have a couple of columns and we have 3 rows here. So basically I'm creating a rank 2 tensor flow in TensorFlow. I'm just giving a constant values populated into this matrix here. And then I'm going to be able to print it out here, so we can take a look at this data matrix for SVD here. So we're able to see what values that we just populated for the float 32 type data type of this. And then there's already, like, if you're going for TensorFlow, you have a lot of built-in functionalities for even performing the singular value decomposition. So we have a tf.linalg.svd, which is basically a built-in function in TensorFlow that computes your singular value decomposition of any matrix. So we can apply that. So basically, it's going to take the arguments of this particular tensor and it's going to come up with the return values for that after the computation. It goes to the function and calculates, and it's not just necessarily a simple matrix like this. You can even get a scalable matrix. You can create the whole matrix with the words as rows and your hashtags as your columns as well. So you can scale it up to any amount of based on your hardware and other aspects there. But so there's also another function in Python for a NumPy that's linalg.svd as well. So you can leverage that as well if you're actually going to implement this in Python instead of implementing in TensorFlow. But it's completely up to you. So for this particular example we're looking at here, so we're taking a look at TensorFlow implementation. And it's a very simple case I'm talking here. Nothing super complicated here. So we just saw that we created a data matrix called SVD here. So we're going to send this data matrix. So we're going to create something like diag D and then orthogonal of U and orthogonal of transpose. So we're going to take this function, built-in function, linalg.svd. We take our rank 2 tensor that we just created and populated with some constants in it, and then we're going to enable the full matrix values and a computation for it, and we're going to simply print that to see how it appears. So basically we're going to compute a diagonal matrix of this 1 by 2. So these are the values we're getting out of it, and then we're going to go for creation of an orthogonal matrix U of size 3 of 3, and then we're going to get these values populated for that. Then we're going to take a transpose of that. So V of t is a transposition. So this is what we get in here. So now basically our attempt is to reconstruct this by passing the values updated from the orthogonal matrix U and diag G and then the orthogonal matrix and the transposition of matrix V, which is V of t. And we're going to try and reconstruct and see if you're able to now get to prove that LHS is RHS, basically to see that our singular value decomposition algorithm holds good. So basically here, based on the values that we computed in the earlier stage here, so I'm going to pass that back to orthog U here, and then I'm also going to pass the values we computed in the earlier iteration as a diag D here, and then I'm going to compute the orthog V transpose as the constant value here, and so then we're going to be able to compute the matrix UDV of T here, which is basically the tensor dot product for these matrices, and then we're going to apply a predictor here to be able to apply this on the rank tensor. So we see here is the orthogonal matrix, and here is our diagonal matrix. Now we're going to actually be able to transpose this matrix and then to reverse this up, and we see that now the SVD proof as the RHS is LHS. So this is where we started earlier. We're able to prove that. So actually the singular value decomposition works. So you can also get more information from the recent release of my book as well for several such examples before you actually get into complicated or advanced large-scale data sets that you want to implement for with text or text mining or natural language processing and things like that. Try to implement fewer exercises. You can find a lot of exercises in the books to get started, and you can take it to the next level after you go through some exercises and run through simple test cases like that, which is certainly something of your current education level, where you are at, and your enthusiasm and ambitions you have, you can certainly get there, and you should be able to implement this. If you have any questions, anything, just feel free to comment here, and we'll take a look at that. So basically, yeah, so we have our times up here. So if you have any questions, just feel free to ask. You can also connect on LinkedIn later as well if you have any further questions. Just feel free to come back and come with those questions as well.